Please welcome to the stage your host, Matt Dobrogé.
Good morning, good afternoon, good evening, everyone, and welcome back to the Lattice Developers Conference. What an incredible first day of innovation and partnership for the FPGA development community. Yesterday, you heard about the incredible opportunity around Edge AI in every vertical market from NVIDIA. Today, we're going to talk about going into another level of detail, not only in terms of how connecting to sensors is difficult, but also an opportunity, but at the same time, how do we do it more securely? So I'm really excited about introducing my colleague in marketing, Dan Manser, to the stage to introduce our first keynote. Dan?
Hello, my name is Dan Manser. I'm responsible for product marketing and product planning here at Lattice Semiconductor. Today we're going to talk about sensor to compute into cloud. Sometimes it computes closer to sensors, sometimes it's in between, and sometimes it's more central to the cloud. So we're going to talk about that process of getting the data from the sensors all the way to wherever that compute might be. So yesterday, our CEO, Jim Anderson, talked about 3 trends in edge to cloud innovation. First, we're going to start with the AI at the edge. Now, that's a big market. We're going to focus in on very close to the sensor, milliwatts, very small millimeters, so where you can actually get very, very small. Now, the smaller it is, the harder it is in the fact that you really need hardware acceleration. You can have very limited RAM, and so each of those solutions has to be very custom and tailored. Custom and tailored is something that the FPGA does well. The second thing we're going to talk about is sensor to cloud, the connectivity portion of it. All the diversity of connectivity. There's lots of different ways you can connect, and there's lots of different topologies along the way. Then lastly, is you have data coming sometimes far away from a sensor, the integrity of that data, and getting it to a centralized place where the main decision-making might be. The integrity of the data is only as good as the integrity of the output. So we're going to talk about security and how pervasive it is important on the security. So let's start with the opportunity, the challenge, and solutions. The opportunity is really 2 categories we're going to talk about. IoT. There's 43 billion devices out there. 1 billion of them are phones, for example, which we all use every day. And even on phones, you can see there's many sensors to one IoT. In this case, there's 15 to 20 different sensors in your phone to one IoT device. That one IoT device actually communicates only a portion of what comes off those sensors. As an average to all of you here in the room, it's 2 megabytes per 12 hours. That's the communication. And you need a certain latency, otherwise you're going to get frustrated. That's just illustrative of there needs to be a very set of how much data you're going to extract, how much you're going to transmit, and what the latencies for that. We're also going to talk about a whole other category where it's very high bandwidth connections, where there's a lot of quantity and you may be only interested in a small amount of it, or you might be interested in all of it in a raw form for AI processing. In that case, they do it for like training, for example, or looking at huge amounts of data where you're actually looking for anomalies. The second thing we're going to talk about is the challenges. And there's a lot of challenges, but that's also a lot of opportunity. There's the challenge where you want to have the compute very localized, and usually, once again, very, very small, very, very low power. And there's other places where you want to take tens or hundreds or thousands of sensors and do a central place where you actually can make some decision making. And last, we're going to talk about solutions. And solutions, there's a lot of solutions out there. We're going to talk about a couple of them, and I'll hint about that, FPGA solutions. We're going to talk about the diversity of data types and how to translate and packetize those data types. We're going to talk about the diversity of the communication types, physical layer, as well as the number of different kinds of connections, and what kind of solutions we can offer in the FPGA community to help that. So let's start off with the opportunity. So we categorize it into 3. We talked about the IoT. But really looking at what are the drivers. Machine to machine at large scale. That's coming more and more. It's going to actually increase both the quantity and the amount of data off those. The next one I really like is automotive. Automotive, if you look at 3 cameras, 3 RGB cameras with LiDAR, that's 2 gigabytes per minute. So that obviously can't all be sent back to the cloud. It has to be centralized and compute in your trunk. And so the topology of the network that's needed inside the cloud needed inside the car is going to change dramatically. And as we go to more and more autonomous and more processing for that. And the third megatrend I want to talk about is really factory automation. Factory automation we've seen dramatically change on the type of connectivity within the factory and the needed QoS or latency requirements is going up substantially. The next trend we're going to talk about is advanced human interface. And here, whether it's a client like a laptop or driver monitor subsystems or industrial or security, now the cameras are looking at you. The last 5 years, we've seen a lot of connectivity to cameras with Zoom and Teams. Now, I think in the next 5 years, you're going to see a lot more innovation where the camera is paying attention to you, make sure you're paying attention, you're attentive, that there's a safety issue, or you're looking at the equipment, or you're driving properly. Then the third really example we're talking about in the opportunity is the bigger AI gets, the bigger the need is for data. And I like to look at examples like radar, medical, or scientific, or metaverse. And those examples taking huge, almost unprecedented amounts of data. In some cases, you're taking all the data to do training. Sometimes you're actually filtering it very quickly, something the FPGA is very good at, and taking only a small subset of that data or doing something very fast in latency or real time for surgery. So what we see is the market is expanding. It's growing and growing. And not only is the market of sensors growing, but also the amount of data that comes off is actually going at a higher rate. You can see that on the right-hand side. So next, let's look at the challenge. Now, we saw yesterday, and I'm going to quote NVIDIA on this, sensors are not built to talk directly to computers. Sensors are not built directly to talk to computers. So we have to kind of break that down. One is the data types. The structure of the data coming off sensors, and there's a large variety of sensors, and the quantity and the quality, sometimes you want to have just a little bit of that data, sometimes you want all the data, sometimes you don't want any ISP, and sometimes you want the entire raw image so you can do training off that. So there's a huge amounts of different types of data types. And then of course with that is the connectivity. We kind of break that down between the sensor to the edge compute to some level of aggregation, sometimes thousands of sensors, and then not just a single cloud, but multi-cloud. So you're going from end to end, and the challenges are with that. So what's best to do is actually break it down to a few examples, and that's what we'll do next. Let's look at robotics, wireless, and camera. And it's nice to see those three because all of them really have a difference in the way they do data acquisitions, whether it's precision sensors, high-speed ADCs, have a very different type of data acquisition. And likewise, if you're doing off-image sensors, you have ISPs or fusion of those. It's very different than the digital front end that you'd see in a radio type application. And then behind that, you even see much difference between the connectivity or the real-time type of processing versus the baseband type processing or classic embedded processing. So each of these applications, we're going to step through and look at how the FPGA can help in the diversity of those kind of connections and those kind of processing and how we move compute closer to the sensor. So let's start with robotics. With robotics, you're going to have to look at the industrial industry as a whole. So we're going to start with that. So on one side there, you can see factory automation. And obviously, every factory is different, but even layers within the factory are very, very different. A lot of them have a lot of legacy. A lot of them have forward-looking requirements. A lot of them have a certain QoS or latency requirement. And a lot of data is extracted into the cloud. So unto its own, it has its own cloud aspects. And within each one of those, there's a different need for connectivity. So you have many different kinds of connectivities. And within any one of them, you actually have many fragmentations of that, as you can see by industrial Ethernet. Lots of different types, and some legacy types. So what the FPGA is very good at doing is connecting a lot of different types of sensors. We've seen this a lot in industrial. We've seen a lot of growth in industrial. And then also a lot of different types of way to connect to the compute. TSN is an example. TSN, over the last, 10 years, has really changed, and there's 37 different SKUs or extensions to that protocol or profiles to that protocol. One profile for being industrial, one profile for being A&D. So you can look at just the history every year that standard has morphed. And it just shows you an example how as people want to get more diverse, not less diverse, and actually do more specialty processing on that connectivity. So let's double click that yellow box, the FPGA. What does the FPGA do and how does it add value here? So on one side, obviously you're connecting sensors. Many times you want to do fusion on those sensors. And on the other side, we want to connect to either a display or to any type of network or compute. And that varies quite a bit on that green line there. But in some cases, because that compute may not be ready, you need to do some buffering, either in the device with the embedded RAM or with an external DRAM. You can see examples of that here at the Developers Conference. You'll see developers of all these connections. There'll be examples of MIPI, there'll be examples of DDR4, there'll be examples of connecting to the various Ethernet types or JESD types. And then we see, as you move compute closer to that sensor, there's lots of different things we can do inside the FPGA to add value for certain requirements on latency. That would be ISP is one example, multiple ISPs, or sometimes you want the raw data. Could be AI, actually very close to the edge, it's some inference, or it could be actually compression. So you actually want to compress that data to be able to make it more efficient on its transport. Now, what we do to help our community is we basically do solution stacks. Solution stacks, I got 3 of them here up on as an example. There's a Sensa AI stack helping you with that AI application. So we provided complete frameworks and tools and development and examples. We have mVision, which actually helps with the signal processing, and it's a solution stack for that. And last but not least, we have Automate, which actually has a lot of the connectivity you'd find in the factory automation type environment. We actually kind of bundle that together and put a whole bunch of offerings there for you. And we actually release these every year. So you can see these actually as the market evolves, we evolve with those standards. And that's one of the nice things about FPGAs, again, is that they adapt. They can adapt quickly, they can adapt to change, and they can handle that diversity. So let's go one step further. Let's take this and actually show real examples you're going to see here at the Developers Conference. So we're in collaboration with NVIDIA and Lattice. There was a talk about that yesterday. But I wanted to highlight a few points. Now, first of all, just on the right-hand side, you see kind of the image sensor connectivity. You can see a connector there on the board below. And you can also do RF connectivity. So it's pretty versatile. On the back side, there's an FMC connector, so you can put any sort of ADC in there, for example, and communicate across JESD. The FPGA's real purpose in this case is to really packetize and present the data to the NVIDIA platform and put it in its memory so the GPU can execute very efficiently out of that. So between packetizing and all the control that's needed to do that efficiently. What I think is really unique about this is 3 things. 1, Ethernet. Usually it's PCI Express. And PCI Express has its positives and negatives, but it can create a speed bump if you actually can make it more efficient to get that memory into the DRAM as fast as possible and eliminate some of the overhead that you see with PCI Express. So that's one interesting thing. You don't see too many PCI Express cards coming in from sensors. You don't see, too many Ethernet cards coming in with sensor activity. The second one really is the fact that because it's Ethernet, you can disaggregate it. You can be actually far away at kilometers, or you can be very close on the same board. You can also go to different locality very easily. So the disaggregation between the sensor, or many sensors, and the compute platform is easiest with Ethernet, at least I believe so. And the third trend I really like about this is that you can actually configure the FPGA from the compute platform. It self-discovers. It can actually load images from the NVIDIA platform. And you can do that and change it out whenever you need it. It makes it much more efficient for development. So you can see that board there was originally developed by NVIDIA. We'll be having a last version of that board in the first half of next year. And on there you can see the Nexus device. And that's really because we think that the low power, it's very important that the platform be as low power as possible. And we have a couple different NVIDIA devices, a couple different Lattice Nexus parts to actually offer that connectivity. So the other thing I wanted to highlight about this is that this will be open source. So it's here for the community. It's here to basically make it easier to go from sensors to compute. It's able to enable customers with quite a bit of productivity as far as being able to how you configure the device, how to interface with the software drivers for NVIDIA. Everything will be released, both the Gerber files, the software drivers, the RTL. We want to build a community based on GitHub for this platform. So let's move on to the next example. Wireless. Oh, sorry. Let's move on to the next example. Not quite. Avant X. Avant X is a way that we have to be able to scale that platform up. So the platform you just saw was very low power, as Ethernet, 10 gig Ethernet. Now, as those sensors go up in speed, you're seeing more and more performance required on the JESD or different kinds of sensors or more sensors. Now we're able to scale up from going from 10 gig to 25 gig. And as you scale the connectivity to the compute up on 25 gig links, you also can scale up the amount of memory you need, the amount of DSP you need, so we can bring more compute to the FPGA with increased high-speed DSPs as well as memory. Now, also what you saw earlier in the industrial, we can also take those 3 stacks we talked about earlier, and we're going to scale them up for this kind of connectivity. As the connectivity goes up, we'll release additional versions of Automate for improved and higher performance connectivity. And as your AI goes up, we'll also be releasing solutions inside the AvantX. So we're really excited about announcing here at the Developers Conference, AvantX. So now let's move on to our second example. Wireless. Going from antennas, or ADCs, what comes off those antennas, and connecting through JSD onto, once again, an FPGA platform. And in this case, connecting through PCI Express to an NXP baseband solution for small cell. And you'll see that here at the Developers Conference, both the connectivity to ADCs, or digital front ends, and connectivities to baseband entities. In this case, it's small cell. So small cell, once again, of course, is very small, very low power. And within the solutions we offer there, we also have an ORAN software stack. You can see the logo up there in the top to the right. And we offer some solutions that you can offer on the FPGA from an RTL and software on that. So once again, similar to what you just saw before, in the industrial space, we can scale this up as you go from small cell to larger cells, or just the diversity of wireless is immense. The heterogeneous networks that are out there, there's lots of different connectivity schemes. Now we can scale up from 10 gig JSD up to 25 gig JSD, and you can scale the connectivity up to 25 gig rates. Either it's PCI Express Gen 4, or you can do you can do eCBRI, or 25 gig native radio over Ethernet. And once again, we'll scale up our software stacks along with that, and we'll also scale up the memory in the DSP along with that. So now let's look at our third example. This is basically camera sensors to compute. This can be applied to many different industries. This particular slide is really referencing to our client. You're going to see lots of examples of the client here at the Developers Conference. And there's lots of diversities in different types of clients, and there's lots of different needs within that. And so sometimes they just have multiple cameras where you can do MIPI aggregation, and really the ISP is done on the host compute platform. And in some cases, it's done connected to, instead of MIPI, over USB, because you can maybe lower the interconnect within the laptop constructs. You can also change out just from aggregation of those video streams to adding AI to it, or you can actually put in a very specific ISP as you change out different kinds of sensors. You may want to change out the ISP. This gives our customer and client customers the possibility to do a lot of different models and a lot of different functions they could have, and a lot of value added they could have and offer to their end customers, whether it's for, once again, the Glance software stack. You can see at the top there we have Glance, and we have Envision, where we actually help our customers or end customers develop platforms that are optimized for different client type of platforms. So with those 3 examples, I wanted to also kind of highlight security. And security needs to be pervasive across all those we just talked about. Security is inherent in connecting many different users or many different types of sensors at one point to not just one cloud, but multi-cloud at the other point. As you have end-to-end, the challenges we all have in this room for security go up. And you know what? We can't solve every security problem. We definitely want to make sure that we can be the best in class for the integrity of the FPGA, but also for things like root of trust or any sort of security of data in motion. And it depends on what device and what platform, but we offer solution stacks in Sentry. And Sentry offers some of the solutions we have to offer you relative to a starting point for your security solutions. But we do see security as the #1 investment priority in global organizations. So putting all this together, we talked about the Nexus platform, kind of our low power leader. We also talked about scaling that up in performance with the Avant platform. And then we put on the sort of the productivity tools, which is sort of easy to use design tools for programming the FPGA, but also productivity tools for doing additional things like you can build a RISC-V in minutes with Propel. Or we talked about the human interface with Glance and some of the complete firmware and solutions we have for that. And then on top of that, we take, we talked about Sense AI or Sentry or Vision. We do these solution stacks, and together we bring this portfolio together, and that's really what we wanted to highlight here at the Developers Conference, is taking parts of that at any level and putting together solutions. And you're going to see lots of those solutions. So as we look through, you can, I wanted to highlight, there's quite a few demos we have here, And you'll be having opportunities to hear from each of our partners on those, but also all our customers with the presentations and panels. So what I'd like to leave you with is really 3 key points. One is sensor to compute. That's going to be with us. We depend on it every day. What we can do to help with that, with FPGAs, is really the opportunity to improve data movement and efficiency and move compute locality up closer to the sensor or give you the options for that. And what we really see is FPGAs offer the most flexibility for those evolving diversity. Once again, diversity is a good thing. What we can do is within that diversity, bring in whatever is the lowest latency, lowest power, and small size and secure. And those are the problems we're trying to solve. And hopefully you see that here at the Developers Conference with Lattice. I want to thank you very much. Matt, back to you.
Thank you, Dan. That was awesome. And thank you for all of that detail for our developers community. And thank you, our audience. We'll be up shortly with our next keynote, so stay tuned. Thank you so much.